Hey guys, so for today, we would be taking a dig at this problem of perfect squares, and it states that given a particular number, we have to find the minimum number of such perfect squares that we can use to add up to get that number. So what do we mean by that is that if the number is 12, we can add 12 ones to get to that number, and or we can just add 4 plus 4 plus 4, and the minimum number of such perfect squares is obviously 4 plus 4 plus 4, which is 3, and so our output would be 3. And the numbers that we are adding up to get to our target value would need to be a square number. That is why it is called perfect squares, and we cannot add numbers like 5, 7, etc. to get to that target value. The numbers can only be 1, 4, 16, similarly all those 9, all these perfect squares. So that is it for our problem description, and let's get on to finding our solutions. And for the solution, we need to build a decision tree and see how it works out. And we know, like, for a number n, we have to use only the perfect squares 1, 4, 9, 16, etc. to get to it. And what we have to do is recursively just keep using that thing until we reach the number, right? So if say, then we have to use 9, etc., and if we haven't still reached to that number, we are again going to use 1, 4, 9, etc. Till the point we have reached to that number. And what I mean by that is that, let's take this example of 12. Obviously we can start off with 1, and we can keep adding 1 to itself till we'll have 12 ones. That is one possibility to get 12. And the other possibility is we have 4, and then we check if adding 4 to that 4 gives us 12. It is 8, which is less than 12, so we keep adding the numbers till we have the total sum is less than the number n, and then we add 4 again to itself, and we see that we have reached 12, and we count the number of such numbers that we have used, and that is our value. Now what if we have got 13? So here we have 12, so it is insufficient, and we add another 4 to it, and obviously that exceeds 13. And what we need to do is that whenever something exceeds our value n, we cannot continue on to that path, and we go back to that previous path and check if we can continue. So in our previous path, like, can we use 9 to get to the 13? Obviously still it exceeds. Now can we then we go back to previous and see if we can use 9, and similarly it's still a lot. That is 8 plus 9, that is 17, and now we have to check if we can add 9 to it, and yes, it reaches 13, and we count the number of these values that we have used, and that is our answer, that is 2. So that, I mean, that is the problem. Now what we are going to do is build up our solutions from an evolution point of view. That is, we are just going to create a simple depth first search solution without any caching, just the recursive thing, and once that works, we are going to use a caching or the memorization top-down approach. And if we understand that, we are going to use a bottom-up DP solution. So let's get started, and let's create a function depth first search, and we will have initially have value or a sum, and let's say sum, and check if so keep it value and check, and count the number of numbers, the number of times we have called in itself, that will be equivalent to the number of numbers that we have, and check if val has reached, and we return the count, and otherwise we will just do something. Now let's figure out, like, how are we going to call this depth first search. So the way we are going to call it is we are just going to add value to s, where s is something we are going to generate in a range of 1 to something, and we will keep adding to that and keep adding to that count. And at the and since we have to calculate the minimum the number of counts that we have, so we'll just use a result that will hold a maximum value. So in this case it's max size, and we'll just check if result is and we just return this result, right? And return we are going to initially start. So this is our initial design, and now we have to figure out what is the value that we are going to provide. So since we are using the square of this number to add to that value and checking it, so obviously the maximum value that we can use if n is the target, so it's square root of n, because square root of n square is only n that can the maximum we can go, and then it will become target itself if n is whatever a square in itself, perfect square. So let's just use that number, and yeah, and yes, now we have another condition. What if the value exceeds n? In that case we are just going to return the max size, right? So yes, that is our initial solution, and hopefully it runs without, I think it's this, and we have an error. The reason being we are not adding 1 to that count. And it works, but it won't work if we are going to submit this, because obviously this doesn't have any caching to it and will throw a time limit exceeded error. And now we have to think how to design something. Yes, it has thrown that error because obviously it is recursively checking, and for a higher value it has to check n to the power n number of times, where n is the uh, number, a square root of n, and in the number of depth it can go n to the power square root of n, that is the number of times it has to check. So the next part is that okay, regarding that n to the power square root of n, I mean, correct me if I'm wrong, but I think that is the time complexity of this solution. And now let's get to that designing the caching technique. So if we have this number set 12 and we are starting off with 4, and we know like we are going to need 8 to get to 12, and if we know like there are two numbers that can lead to 8, so how many in that case will lead to 12? That will be 3, right? Because there is one perfect square that is 4, and there are two perfect squares that leads to 8. So if 4 plus 8 is 12, we are going to add these two perfect squares, number of perfect squares that each of those numbers constitute, and we will arrive to that solution. So that is the caching technique. So to give it more info, let's say we are starting off with 12 and 4, and each node has a value, right? So if we are going to 12 and we are going to hop to each node and check if it has become 12, we are going to, every time we are going to have to check, add and check. Instead what we can do is that each of those nodes can actually hold the value and the number of such perfect squares that such value constitutes. So after 4, and we are going to check how much we are going to need to get to 12, that will be 8. We are just going to jump to that perfect node and check the value, and we are going to add that to itself, which is 1. and we are going to return the value. So that is the caching. And to give one more example, it will be like this. So on top we have the numbers 0, 1, 2, 3, 4, 5, 6, 7, etc. And then we will have the number of perfect square that we need to reach to that value. So for 0 it is 0, for 1 it is 1, for 2 it is 1 plus 1, that is 2, for 3 similarly it is 3, for 4 in itself we need 1 4, and for 5 it is, now we can see that for 5 we are starting off with 4 or we can start off with 1, and once we start off with 1 we have a count of 1 because we now have only one number. And now we check how much we need to reach to that 5. We need 5 minus 1, that is 4, to reach to that 5. Now we know like there is only one count of a particular number that can give us 4, and since we already have 1 and we need one more, so the 5 will be 2. So this is our caching. So for 6 it is again 4 plus 2, that is 3, and for 7 it will be similarly 4. And we this is the technique, and now let's get on to coding this thing. So let's create a DP cache for this thing, and what we are going to check is if we are not going to need this part, and if we are going to check if target minus the current val is in DP. If it is, then we are going to just return, right, and we are just going to put the target in here, and if val is target, instead of in we are just going to check target, and I think that is about it. So what is target? We know like 12 is a target, and now what we are going to do is that for to go to 12 we are going to calculate the number of numbers that we are going to need to reach a particular value, and keep figuring out that number. So in that case we will be able to cache this 8. So we are going to generate all the numbers that we are going to need to get to that n, and we are just going to create a cache of target, and every time we are going to check if the value is present in DP, we are just going to add and return to it, and at the end we are just going to return the val of target. That is all. So let's check if the solution runs without any bug, of course, and we have invalid syntax. We need an if. We need to pass target. So yes, this solution runs. Let's submit it. Cool. Now we have our top-down memoization. Let's check how we can create a bottom-up back DP solution. And we are just simply, going to copy this thing and put it here. The thing is very obvious. Obviously, our bottom up solution can be arrived from here. So it is the same. All we need to do is this, and instead of this, what we are going to do is dp of, again, target minus s into s plus dp of s into s, and we are going to just return -1. Now, what is this target of s into s? We already know that is val, because val was s into s, so we are just putting it here. Now, what is dp of s into s? That is the count, right? So every time we were achieving that thing. So in this case, dp of, say, let's say 6 is 4 plus 1, sorry, 4 plus 2, and in that case first s will be 1. But think of it, if s into s is the dp, then it will always be 1, right? So any number that we can get that is a perfect square, it will always return 1. So for example 16 will also return 1. So if we are going to get, we can keep it like this, or we can just say it is 1, and we are going to need to initialize dp, and we are going to put our base case, that is dp of 0 will be 0, as we know, like, there can't be any value for 0. And yes, we have a solution. So let's check this thing and let's submit. So there you have it, guys, all those evolution of the code from a simple recursive to memoization to top, bottom up. So thank you for this session.